In the last lecture, we had talked about the first two postulates of quantum mechanics. The first postulate was that every physical system is represented by a ray in an abstract inner product space known as the Hilbert space. The second thing that we did is to point out that there is really no difference between a state which we represent by, let us say, ket psi, and another state which is represented by a scalar multiple of the same state psi, where the scalar multiple is in general a complex number. And because of that, the states are actually represented not by a given vector in the Hilbert space, but by a ray in the Hilbert space. Having done that, we had defined operators which are linear operators in the vector space, and towards the end of the lecture, we were telling you that there are matrix representation possible both for the state, that is vectors, and the operators which act on this space. We had seen that a general operator has a structure like a ket alpha followed by a bra beta, so that it can act on an arbitrary vector giving me another vector. Now supposing these two have the same dimension. If these two have the same dimension d, then this is a product of a column vector with a bra vector having the same dimension. So if this is a column vector of d dimension, that is there are d entries in the column, and if this is the bra vector, then I get a d by d matrix. Now you have to realize that this is not an ordinary matrix multiplication, but is what is known as direct multiplication of matrices, or also known as Kronecker product of the matrices. Now the way it works is something like this. Supposing I have a matrix which is, I write as A11, A12, A21, A22, and try to multiply this with a matrix which is, let us say, B11, B12, B21, B22. Then the way this product works is, you take the element A11 and multiply with the matrix B itself, and similarly A12 with B, A21 with B, and finally A22 with B. Now this, of course, you have to now expand it out, and I will not write down the entire 4 by 4 matrix, but the way it goes is like this. So I have a A11 multiplied with this 2 by 2 matrices, so I will have a B11, A11 with B12, A11 with B21, A11 with B22, and like this I have, so it will become a 4 by 4 matrix. So this is what is meant by a matrix product or a Kronecker product. Now we talked about that physical observables such as energy, angular momentum, etc. are represented by self-adjoint or Hermitian operator. Both the languages are the same. Now according to this postulate of quantum mechanics, which I still insist on calling it second postulate, a state psi has a definite value lambda I will explain what it means by that. Definite value lambda for an observable. What it means is that supposing I am interested in finding out what is the energy of the state psi. So my observable is energy. Now then, if I measure the energy of psi, then I can make a statement that the energy has a particular value only if this state psi happens to be an eigenstate of the operator corresponding to energy with an eigenvalue lambda. So the postulate simply says that supposing you have any observable A, or this is operator corresponding to the observable A. Now if this acts on an arbitrary state psi and gives me a number times the same psi, then this lambda is called the eigenvalue of the operator A, and the corresponding psi is called an eigenvector corresponding to this eigenvalue. Now an arbitrary state is not necessarily an eigenstate of an operator, but if you take the collection of eigenstates corresponding to a given operator in the Hilbert space, then this set of eigenstates, they form a complete basis. What is meant by a complete basis? It simply means that an arbitrary vector in that state can be expanded in terms of the eigenstates of any operator corresponding to whatever observable you have. In other words, I can expand an arbitrary state in terms of, let us say, a complete set of eigenstates of the energy operator, or I can do the same thing in terms of the complete set of eigenstates of, let us say, angular momentum operator. Now, so suppose I have identified one particular observable in which I am interested in. No particular reason, but let me for specific purpose call it an energy. So I am interested in finding out what are the eigenstates of the energy operator. Now, and I have determined the complete set of the eigenstates. Just to give you a familiar example to you, that you have solved the problem of hydrogen atom and found out that there are possible energy levels which are given by the Bohr's energy condition, the ground state having an energy minus 13.6 electron volt, the next higher states having an energy minus 13.6 by 4, the next one minus 13.6 by 9, etc., etc. Now each one of these, the state corresponding to each one of these values are called eigenvalues, is an eigenstate corresponding to that eigenvalue. So what we are saying in this context is, an arbitrary state of the hydrogen atom can be expanded in terms of these eigenstates corresponding to definite eigenvalues. And what this the postulate said is that when I make a measurement of the energy, then the best I can do is to predict the various probabilities with which they will occur. And I cannot definitely say if you do a measurement, you will get minus 13.6. Now, one can show that if we consider a normal matrix, actually the theorem is, I am interested in that theorem for only the Hermitian matrices, but in practice the theorem is actually true for much more general matrices called the normal matrices. Normal matrices have this property that A dagger A is equal to A dagger. Now if you look at that type of matrix, and if you look at any normal matrix, there is a theorem which is called spectral theorem, and the spectral theorem simply says that this matrix or the operator and the matrix, they will be used interchangeably, can be expanded in terms of like this: the eigenvalue corresponding to the operator A times another operator called Pn, and this Pn is a projector. The Pn is a projector corresponding to the eigenstate lambda. Now if you think about it, it's not all that difficult to understand what it means. See, basically we are saying that if you have an operator, now you can resolve that operator into various operators which project a state along a particular eigenstate. And spectral theorem simply says that. Now, so obviously there are some properties to be satisfied by these operators, these projection operators. So one of them is Pm times Pn is delta Mn, means if you multiply, actually Pm times Pn is delta Mn times Pn. There is a mistake in that slide. So Pm times Pn is equal to delta Mn times Pn. Now this is actually obvious, because once you have projected in that direction, these are orthogonal projections. Once you have projected in, let us say, direction n. Now if you now try to project something in the direction m, obviously it is going to be 0 unless it is in the same direction. And if it is in the same direction, then Pn square must be equal to Pn. The other thing is that these operators are Hermitian, matrices are also Hermitian, and secondly, I must have a completeness, that is sum over n Pn must be equal to I, because I am resolving an arbitrary operator in terms of its orthogonal projections. So obviously when I add up all of them, they have to give me the same identity back. Just to illustrate the spectral theorem, let me look at the basis in C2 again. The C2 is one where we keep on coming back with various types of bases. I have told you that C2 has a basis which is 1, 0, 0, 1. But let us look at another basis in C2. This is normalized basis, 1 over square root of 2, 1, 1, and 1 over square root of 2, 1 minus 1. In other words, in terms of these two bases, I can expand any vector in that two-dimensional space. Now these vectors are eigenstates of a matrix which looks like 0, 1, 1, 0. We will later on see this matrix has a very important place in our physics that we will be doing. Now, so this is an eigenstate of this operator with an eigenvalue, let me write it as lambda equal to plus 1, and this one corresponds to lambda equal to minus 1. You can easily see the eigenstates of this is plus or minus 1. So this has eigenvalues plus or minus 1. Now let us look at what does this spectral theorem say. So first one is, supposing I call it E1 and supposing I call this E2, then my operator P1 corresponding to this eigenstate is E1, E1. This is the general structure, and you can immediately multiply. So I have a 1 over square root of 2 into 1 over square root of 2, which is equal to 1 by 2. I multiply 1, 1 with 1, 1. This is a direct product, so therefore I get 1 by 2. You can see 1 into 1, 1, 1, 1, 1. This is P1. And the corresponding thing for the other eigenvalue is E2, E2, and that's equal to 1 over 2, 1 minus 1, 1 minus 1. You can multiply these easily. So I get 1, minus 1, minus 1, and 1. So these are my two projection operators. And you can immediately see what I am trying to tell you in the spectral theorem is that my original matrix, which is 0, 1, 1, 0, is given by lambda 1, which is equal to 1, into the first projection operator, which is 1 by 2, 1, 1, 1, 1, plus minus 1 times 1 by 2, 1 minus 1, minus 1, 1. You can see that this does indeed give this one. So this was my second postulate, and we have done some linear algebra with it. Now I come to a rather important philosophical process, which is a component of Copenhagen interpretation, which was the most contested component of the Copenhagen interpretation by, as I had told you in the beginning, even by Einstein. And this is what is known as the wave function collapse. Now, the wave function collapse is a postulate which has certain amount of philosophical significance. Let us try to understand what it means. So, what we said in the beginning is that if I look at an arbitrary sket psi, then I can write it as a linear combination of Cn psi n, where these psi n's form a complete set of eigenstates of corresponding to any operator. Okay, complete set of eigenstates of any operator. Now, supposing I have a system in this state, and I have expanded this in terms of complete set of eigenstates of an operator. Let us again, for specific idea, let us say it is the energy operator. And I now, using this state, I want to measure the energy of the system. What the Copenhagen interpretation says is the following, that the result that you would get when you make a measurement of the energy will be one of the possible eigenvalues of this set. Remember, we said psi n's are complete set of eigenstates, means the psi 1 corresponds to lambda 1, psi 2 corresponds to lambda 2, etc. So, what we are saying is that if you take a measurement of this state, I cannot tell you what will be the result I will get, but I can tell you that you will get either lambda 1 or lambda 2 or up to lambda n. And I can say, do something more. I can say that the probability with which the value lambda 1 will occur in a measurement will be given by C1 square. Likewise, probability with which lambda 2 will appear will be given by C2 square, etc. And in general, this Cn square, you can easily see by definition of my projection operator, is nothing but psi Pn psi. And Pn then is nothing but, supposing I represent lambda n, I had written it as psi n, does not matter, as the projection operator corresponding to the eigenvalue lambda n, then this is what the probabilities are. So, on making a measurement, the wave function of the system would suddenly collapse to the eigenstate corresponding to the eigenvalue that you have measured. This is called collapse of the wave function. Now, what it means is something deeply philosophical. It tells you that quantum mechanics has two parts. One, when no observation is being made. What happens there? How does the wave function change? Which I am going to talk in a moment. But a process of measurement is a totally discontinuous process. During that process of measurement, the state of the system would collapse to one of the eigenstates of the system. And there is no way anybody can predict which eigenstate it will collapse to. The best that one can do is to tell you that this will be the probability with which a particular state will appear. Now the question is, how does one calculate such a probability? That is also another problem. The way to calculate such a probability would be to make identical copies of the system, large number of them, and make the measurement over and over again on different systems, but identical, and find out how many times, for instance, lambda 1 is appearing, how many times lambda 2 is appearing, etc., etc. We will see there later that this is itself a tall order, because there is a theorem which says you cannot make identical copies of a system. But that's a different story. That's a philosophical question. Now, what happens to the state of the system once it had collapsed? So we have agreed that what has happened is that the state has gone from state psi to a projection of the state onto the eigenstate corresponding to lambda m. Now, if I now normalize this state, I can talk about what is the post measurement state of the system. And this is given by P and psi, and I need to normalize it simply, which means I will divide it by its length. So this will be psi P n psi, and you can see why, because this should be this quantity multiplied with the corresponding bra, but then I will get a Pn square, but Pn square is Pn, so therefore this is the structure. So this is the post measurement state of the system. Let us look at a matrix example to make it very clear what is happening. Supposing I have a state which I have normalized it, 1 over square root of 5, 2, 1. Remember, normalization simply means square of this, 1 divided by square root of that sum. So supposing I have this state, I want to expand this in terms of the eigenstates of that matrix which I talked about, the eigenstates of 0, 1, 1, 0, which was, I had taken this to be 1 by square root of 2, 1, 1, plus, so I write it as a C1 plus C2 into 1 over square root of 2, 1 minus 1. Now this is easy to calculate what is C1 and what is C2, because this is a matrix identity, so I just put this whole thing, and you can do a trivial algebra, and so C1 is equal to 3 by square root of 10 and C2 is equal to 1 by square root of 10. Now, what it tells me is this, that if I make a measurement and I get the eigenvalue to be lambda equal to 1, then the post measurement state of the system, its normalized value, will be 1 over square root of 2, 1, 1. So this is the third postulate. I will complete the quantum postulates with a fourth postulate, which is, I will not be using it much, accepting philosophically that when I am not observing a system, what happens? When I am not measuring a system, what happens? The time evolution, so I will call it postulate 4 for convenience. Remember, postulates are hypotheses on which a theory is based. So therefore, you don't question where did it come from. So time evolution, how does a state psi develop with time? What it says, it follows an equation. Remember classical physics, we say that the evolution or the with time, the dynamical quantity follows Newton's law. In this case, the corresponding equation is known as a Schrodinger equation. Which is given like I h cross d psi by dt is equal to h psi, where h is the Hamiltonian of the system, Hamiltonian operator of the system. You can do a formal solution of this and find that psi develops with time following an unitary operator. I should write psi t. And a formal solution for u of t is e to the power minus I h t by h cross. Now, this is an important point, that the unitary operators, the operators which determine which way a state will develop, are operators which are unitary operators. Now, what is the unitary operator? An unitary operator is an operator which preserves the norm of a state or a vector. So, just here is the definition, that u psi is equal to phi. If this is what happens, the operator u is unitary if the state phi and state psi have the same norm, that is phi phi equal to psi psi. Now, this automatically implies that u dagger u equal to I. I is an identity. You can check, for instance, that this is a unitary operator. This is a unitary matrix. Now, what is important take in this last one is that all quantum processes develop unitarily, and as a result, the operators which we deal with in quantum computing are all unitary operators. So, these are the operators which decide how a state develops with time when you are not making a measurement. The process of measurement makes it a discontinuous process, makes the state collapse to one of the eigenstates of the system, and so therefore, the quantum computing deals with two aspects of this computation process. One is, just to give you a classical analogy, it means that when it is passing through transistors and gates, I am not trying to find out intermediate results, I am perfectly alright. The system simply follows a unitary operation. But the moment I decide I want to do a read, find out what is the result, I must make a measurement. And when I make a measurement, I can at best give you a probabilistic answer. And the result that I will get will be one of the permitted results. But I have no way of telling you which result I will get. And this causes a big difficulty in extracting information out of the measurements, because we are interested in only relevant information. We will see as we go along how one gets it done.